with a primary mirror diameter. So it will have its main mirror will have 39 meters diameter. That's about half the size of a football field. And the whole dome and structure is really the size of a football stadium. So you can see some people at the bottom of this artwork, and some lorries and cars. So that gives you a rough idea of the size of the structure that we are thinking of building. And so the main purpose of my talk today is twofold. I'm going to explain to you a little bit about the ELT. But before I do that, I'm going to try and explain to you why astronomers build such large telescopes, or why do we build ever larger telescopes. And somebody was asking me before, what does it feel to look like with an eyepiece through one of these? And unfortunately, we don't use eyepieces with professional telescopes. We just take pictures or spectra. So nobody's actually looked through a large telescope to see what it feels like. Okay, so this is a sort of rogues gallery of the telescopes that are out there at the moment. Today, the most famous ones are the 4 VLT telescopes here in the Southern Hemisphere in Chile, also run by the European Southern Observatory. Then there are the Keck telescopes that are on a mountaintop in Hawaii. The LBT, or the Large Binocular Telescope, which is in the continental US on Mount Graham, and a lot of smaller telescopes as well. So unfortunately, I think astronomers are not very imaginative in terms of the names we give these. So the current generation, which is already working for 20 years in Chile, is called the Very Large Telescope. The one I'm going to be telling you about today is called the Extremely Large Telescope. And in fact, we did have one which was even bigger. There was a plan for a 100-meter telescope a few years back, and that was named OWL, which stood for overwhelmingly large. Right? And the joke today is that because that was cut back because of funding, and is now essentially become the ELT, that our joke is that OWL now stands for originally was larger. So why do we build enormous telescopes? Two reasons. One is that bigger telescopes have more collecting area, so more light gathering power. So this allows us to study objects that are fainter. And I'm often asked, how far can you see with a given telescope? And there's no real limit to how far you can see. It really depends on the brightness of the object. So if we have a very bright object, we can see it all the way to halfway across the universe. But even sometimes there are faint objects which are really close by, like planets orbiting other stars, which are fairly close to our own. And so in that case, again, the power of a large telescope allows us to see these really faint objects. So fainter usually means more distant, but not necessarily. But in the case when it does mean more distant, because the light has taken a long time to travel from this very distant object to us, we see these galaxies or stars as they were a very, very long time ago. So the light travel time is of the order of billions of years. And so we see these as they were in their youth, in their infancy, so to speak. And so we see these objects as they were younger. And so by looking further and fainter, it also allows us to use these telescopes as a kind of time machine that allows us to see objects all the way back to the very early history of the universe. So you can see here on this plot, for example, this is today over here with our satellites and space telescopes. And the earliest that we can see, which is the first generation of stars that lit up the universe some 400 million years after the Big Bang. We can see all the way back to there with the newest generation of telescopes that I'm going to be telling you about. So here's another way to see where the ELT fits in with respect to the telescopes we have today. And you can see that one of the axes here is just the year in which the telescope has been built, and the other is altitude, simply to sort of separate the points. But if I put the ELT on the same plot, you can see that it dwarfs all existing telescopes. In fact, it dwarfs them to a point where if you combine all the collecting area that mankind has ever built to date, then that area is almost equal to that of the ELT. So you can see that the ELT is going to be a huge step forward in terms of how faint an object we could see. Okay, so let's do the simple calculation that has gone into the title of my talk. If you look at the pupil of the human eye, it's about 4 millimeters in diameter when when it's dilated for nighttime stargazing, versus roughly 40 meters for the ELT aperture. So that's a factor of 10,000. And if you do it in area, because indeed that's what the light gathering power is connected to, then the area of the circle would be about 100 million times larger than that of the human eye. So essentially the ELT has the collecting area of 100 million human eyes, right? We measure, some of you who are amateur astronomers would know about this, that we measure stellar brightness in magnitudes, with 1 being the brightest and 6 being the faintest that the unaided human eye can see. And it's a logarithmic scale, so 5 magnitudes roughly corresponds to a factor of 100. So if we looked at 100 million, that would correspond to 20 magnitudes. So that would mean that if with the naked eye we can see a 6th magnitude star, with the ELT we should be able to see a 26th magnitude star. Furthermore, we can actually expose for longer, right? Because the human eye, because it's designed by evolution to look for change in the scenery, we can't actually, even if we stare at something, effectively our eye is only collecting light for something like 1/10 of a second, after which you start to sense image motion, your eyeball moves around. With the ELT, if we have a camera, we could easily expose. We don't use photographic film anymore, we use CCD detectors or near infrared detectors, but we could easily expose for something like 1,000 seconds. So that buys us another factor of 10,000. So that would tell us that we should be able to see things that are 30th or more than 30th magnitude. In fact, we can't quite get there because we are limited by the background of the night sky. So the night sky is not really as dark as we would like it to be, but perhaps more about this a bit later. Okay, so that was one reason why we build big telescopes, is because we want to collect lots of light. The other is because we can get sharper pictures. The bigger the telescope, the sharper the picture you can get. And this is the only equation I'm going to put in my talk, which says that the angular resolution, so the angle over which you can discern that there are 2 distinct objects that you're looking at, is connected to the wavelength of light divided by the diameter of the telescope. So if you use the same units for these, this becomes a dimensionless angle. And astronomers usually measure these angles in what we call seconds of arc. So 1 second of arc is 1/3600th of a degree. Or you can think of 1 second of arc as being 1 part in 200,000, roughly. So the ELT's resolution limit will be something like 0.01 arc seconds, so 10 milli arc seconds. And to give you a feel for what this is about the size of a 1 rupee coin held at a distance between Mumbai and Pune. Okay, so that's the sort of angular resolution that our telescopes can will provide when the ELT is built. But there is a problem. The problem is the Earth's atmosphere. So we have this enormous telescope. It's sitting on a high mountaintop in Chile, but nonetheless, it is limited by the Earth's atmosphere. So we can't quite get to this perfect image. Why is the perfect image not just a point, but is even limited by that equation that I had in the slide previously here? So this has to do with the wave nature of light, and this is called the diffraction limit. And I'll try and give you a very simplistic explanation of where this comes from. So imagine this is my very cartoon telescope with a big primary mirror, a parabolic mirror, and this is light from a distant star that is being reflected off the primary and is coming to a focus here at the focus of the telescope. And that's where the blue star image would be. Now, what we astronomers like to think of is in terms of what's called a wave front, because light is a wave. So this ray picture is not quite correct. And a wavefront is denoted here by this horizontal black line at the top. The idea is that a wavefront represents a line joining the crests of all the waves, right? So the waves at different points in space, if you join all the crests of one wave, remember light has a very high frequency, it's about 10 to the 15 hertz. So these waves move very quickly at the speed of light. If you join all those crests, what you would get is called a wavefront. So that would represent this black line. And you'll see in a second why that is important. So the parabolic mirror has the property that the total distance that you measure from this horizontal line along this ray reflected off of the primary mirror and up to the focus is the same for all different light paths. So I've drawn two of them here, but if you drew many other light paths, the total distance traveled coming down to the primary and then back up to the focus would be the same. So because of this very property, then if all of the crests of the waves would line up here at the top, then because the path length is the same, they would also line up at the location of the focus. And what we say is that we get constructive interference from all of these different parts of the mirror to form the telescope sharp image at the focus. Okay, so this is what it would look like if you took an idealized telescope or put this telescope in space. You would get this kind of image of the star. This is what's called an airy pattern after the person who first discovered it. And you notice that it's not a sharp point, but instead it has these rings that go around it that are called the airy rings. So let's try and understand where these airy rings come from. And let's look at this first dark ring around the bright circle here. If you now think of the light as a wave and only consider these two parts of the mirror that I have now drawn in green, then you can see that the light from these two parts of the mirror is going to constructively interfere to form the image of the star. But remember that because light is a wave, actually the light reflected from these two pieces of the primary is not just arriving at the focal plane, it's arriving at every point in this in the focal plane of the telescope. So I've drawn some red lines. These are not rays in the sense that these are not obeying the law of reflection now because I'm thinking about it as a wave. But you can think of the path length that is from this black horizontal line that the red lines represent, which is looking at some point slightly off to one side of the star. And now if we compare the lengths of these two arrows, the red arrows, you'll see that they are not equal, unlike the blue ones, which are equal. And if you now think about the wave nature of light, you will find that at one point, as you move away from this blue star, at one point, these two red rays will have such a path difference that the waves will now destructively interfere rather than constructively interfere. And that will cause a dark ring to appear some distance from the star. The bigger the telescope, the shorter this distance has to be, and therefore the sharper the image, or the sharper the smaller the size of this white circle. So that's a rather simplistic explanation of where the diffraction limit comes from and why no telescope can give you a perfect point-like image of a star. Note that this is different to what you would see if you had a real star located at a different position in the field of view, because for that different star, the wavefront or the rays would appear to come from a different direction, now shown in green, and they would focus following the normal laws of reflection at a point which is slightly offset from the main one. If the distance, the separation between these two stars is equal to the separation between the bright center of this image and the first dark ring, then we have a criteria which we call the Rayleigh criteria, which tells us that actually we can separate the light from these two stars and say that they are two separate stars rather than just being merged together to form one big blob of light. So if you looked with a small telescope, you might see this one blob of light on the right, because the small telescope has a broader diffraction limit, whereas a larger telescope would allow you to see them as two distinct stars. So this is the resolution on the sky, angular resolution, and this is the main other reason why we try to build bigger telescopes. So if you had a telescope like the VLT today, and you had 8-meter diameter, then at visible wavelengths, your limit would already be only 15 milliarc seconds, so almost as good as the ELT that I told you about earlier. But we can't achieve anything like this from the ground typically. And the reason we can't is the atmosphere, right? So the atmosphere causes the stars to twinkle. And in fact, if we did look at the images, this is what we would see. So this is taken with a TV camera at the focus of a telescope. And what you would see are what we call speckles, and they dance around very rapidly. And this is all caused by turbulence in our Earth's atmosphere. So let's look at what that is and what happens. So imagine that it's the same reason why the stars appear to twinkle at night. So imagine you threw a stone into a pond on a quiet day. You would see these circular ripples or waves emanating from the point where you threw the stone in, and they spread out over your lake. On a quiet day, these would be nice, perfect circles. And if you went very far away from them, you could approximate them by straight lines, which is what we do for stars because our stars are so far away from us. But on a windy day, the presence of the wind breaks up these nice circles into something that looks much more turbulent. And in fact, we have the same issue that happens to starlight when it arrives at the Earth's atmosphere. So out in space, Hubble Space Telescope can see these perfectly round waves of light emanating from distant stars or galaxies, whereas an Earthbound telescope like the ELT has to suffer these aberrations that when the light goes through the atmosphere. And so if we zoom in, we start to see the impact that these has. So what does this do to our nice perfect image that we talked about earlier? So let's go back to our cartoon telescope model and look at the impact of the Earth's atmosphere. So this is now our plane wavefront that we would expect from this very distant star. As I said, it's a circle, but it's a circle with a radius of several light years for the nearest star and many 100 million times that for the most distant objects. For all practical purposes, it's a straight line. However, when it goes through the atmosphere, imagine now that the left part of the primary mirror has a cell of atmosphere or a piece of atmosphere above it, which is at a slightly higher temperature than the one on the right. So the one on the right is denser because its temperature is lower. The one on the left is more rarefied and therefore has a lower refractive index. Now the refractive index is the ratio of the speed of light in vacuum to the speed of light in a medium. So when the refractive index changes, which is all due to temperature changes, and these are small temperature changes, we're talking about a tenth of a degree centigrade or something like that, then the light takes longer to travel through this bit of atmosphere, through the right bit of atmosphere than it does through the left. Right. So now the wavefront, instead of arriving at the telescope as a nice straight line, now gets aberrated, and different parts of this wavefront arrive at different times, depending on what the refractive index or the temperature of the atmosphere above the telescope is. And this is high above us. It's about 10-kilometer altitude typically. So maybe a bit less for the telescope on a high mountaintop, but nonetheless, it's that sort of altitude where jet airplanes fly. And this is continuously changing with time as well, because this is driven by the wind at high altitudes, or the jet stream. If you're unlucky to have the jet stream go over your observatory, we typically try not to have our observatories at locations where things like the jet stream would plague us. But nonetheless, we get this aberrated wavefront. And that means that now you can see that this idealized picture we had earlier, which said that the total path length from the straight line as reflected by the parabolic primary to my star image was constant, that is no longer satisfied. So now, instead of getting constructive interference, which would make a nice image of a star, which was a sharp point, I get these little speckles. The speckles come about because different parts of this of the light reflected by the telescope now interfere either constructively or destructively, and this constantly changes with time at about 100 times a second or so. So unfortunately, we don't get this wonderful diffraction limited imagery, which would allow us to see a 1 rupee coin that was held up in Mumbai from Pune. But astronomers have a way around this, right? We have a technique which is called adaptive optics. And adaptive optics allows us to fix this turbulence of the Earth's atmosphere. And we do it by using what's called a deformable mirror. So here's a movie made by the Gemini telescopes that shows you how adaptive optics works, which allows us to get really sharp pictures from large telescopes, even in the presence of a turbulent atmosphere. And as you'll see, we are now looking at the light collected by the telescope coming in here from the top. And this is my adaptive optics system. So I'm going to just pause here for a second and explain to you what is going on. So this is the light coming from the telescope. It comes to a focus here. I have a lens over here which collimates the light and makes it into a parallel beam. So ideally, the wavefronts which would be perpendicular to this beam of light now would be flat here. But in the presence of the turbulence of the Earth's atmosphere, they are not. But I have a mirror, which is called a deformable mirror. So this mirror is made up of a really thin sheet of glass, about 1 millimeter thick. And behind this sheet of glass, I have several thousand actuators with which I can push and pull on this piece of glass in real time, 1,000 times a second. And I can change the shape of this piece of glass to will, such that I can combat the turbulence from the Earth's atmosphere. So let's see how it's done. So the light is split into two. Part of it goes to my science camera with which I want to take images. And you can see that these are these blurred images with the speckles that I showed you earlier. But the other part of the light goes to something called a wavefront sensor. So this wavefront sensor is measuring continuously these distorted wavefronts that are coming in from the turbulence in the atmosphere from a distant star. And now if I close my control loop and I start changing the shape of my mirror in real time, I can turn these distorted wavefronts into nice flat chapatis, right? Or tortillas if you're giving the talk in Mexico. And so now I've turned my speckly image into something which looks perfect or almost perfect back into this airy pattern that I showed you with the nice rings. Okay, so that's the principle behind adaptive optics. So I tried to show you what all these different components are. So the key is to measure the wavefront here with what's called a wavefront sensor. So that looks at the answer you're getting and compares it to the ideal answer that you would have, which would be a flat wavefront for a star. And then applies that correction to this key component, which is called a deformable mirror, which turns those wavefronts into flat wavefronts all the time. So this system is running in real time at our telescope all night long, correcting the turbulence from the atmosphere 1,000 times a second over the whole telescope's aperture. And with that added in, now you can see what the impact would be on our image. So instead of seeing this very speckly image that I showed you earlier, now if I turn on the adaptive optics, it does two things. One is it actually removes the image motion first. And then if I do what's called the high order correction, and then I've turned this into the airy pattern, you can see the airy ring there. You can see the nice airy ring here with the first dark ring that I was trying to explain to you. This is the next bright ring, and the further airy rings are broken up a little bit into speckles because the correction is not perfect. But nonetheless, it does a pretty good job. And so now with the advent of adaptive optics, which is about 20, 30 years old now, astronomers have finally got to the point where with these systems, we can now get diffraction limited or extremely sharp images and realize the full potential of our very large telescopes. Now, those who've been listening very carefully may find that I have pulled the wool over your eyes a little bit with this adaptive optics business, because what I haven't told you is that in order for me to correct the wavefront, I need to know what the answer is, right? I need to know that the wavefront was truly flat to begin with. But if I know what the answer is already, then what's the point of taking an image with my telescope? Because I know I'm going to see a star, right? If there was some structure to my star, then obviously the wavefront would no longer be flat, because all of that information is indeed encoded in the incoming wavefront. The reason adaptive optics does work, despite this limitation, is that we use what's called a reference star to do the adaptive optics correction. And that correction then applies to something else, which is the object of interest that we are looking at, which is located very close to that reference star, but not too far away. And I'll explain in a second why. So what we want to do essentially is to correct the turbulence for this blue cylinder above my telescope, assuming the telescope is looking straight up at zenith, in order to correct the light from this galaxy. Now, very near this galaxy, I happen to have a reference star, and this reference star now shows me this tilted cylinder, and it's the tilted cylinder that is being used to there I know the answer. I know that the wavefront should have been flat. So I can use this reference star to do the sensing of the wavefront, put that correction through my control loop into the deformable mirror. And what I get back then is the perfect image, not only of my star, for which I knew the answer, so it was a bit pointless, but now that same correction also applies to the galaxy. And that gives me the answer that I want, which is a very sharp image of the galaxy on my science camera. But notice that it didn't quite work perfectly, right? For example, this little area up here, which is now in light blue, which was light from the galaxy, which I ought to have corrected, didn't really correct perfectly well, because I wasn't able to sense it, because that part is not, we're not passing through that part of the atmosphere for the reference star. Instead, it is there is another bit of the atmosphere here which only belongs to the reference star, but not to the galaxy, which we are correcting for. But that doesn't really hurt us, but that's not useful to us, because what we're interested, of course, is in the galaxy. So you can see that the adaptive optics correction would work on the galaxy, but it would work as long as the galaxy was really, really close to this bright star, which I could use as a reference. Well, unfortunately, there aren't enough bright stars in the sky. They need to be bright, because I have to do this correction 1,000 times a second, because that's how fast the atmosphere changes and the turbulence changes above my telescope. So while astronomers have been successful in using adaptive optics for 2 or 3 decades now, we have been limited in which part of the sky we can apply this adaptive optics correction to. And it's really only in the very near vicinity of bright stars that it works. So that's a pretty serious limitation for a big telescope, because you can only see less than 1% of the sky with this exquisite angular resolution that we are after. But astronomers have found a way around this as well. If we don't have a real star in the sky, we'll make our own. And this is the idea behind laser star adaptive optics. Okay, so instead of having a real reference star, oh, sorry, I have jumped too far ahead of myself. I wanted to show you this first. This is a mock animation to show you the difference that you would get with adaptive optics between what you would get with the presence of turbulent atmosphere. So this is what we call seeing limited. So that means without any correction whatsoever. And this is now this 1 arc-second size, which is about 1 part in 200,000. So this is 1800th of a full moon that we're looking at here. Okay, so now if we looked with the Hubble, we would see a much sharper image, of course, because Hubble is above the atmosphere and it doesn't have any issues with the turbulence. But Hubble is a small telescope. It is only 2.4 meters across for its primary mirror. And so its diffraction limit is not that great. And therefore, this is the picture we would see. If we now had adaptive optics on our current generation of telescopes, the 8-meter telescopes that we have, the VLT, for example, this is the sort of image you would see. And if you applied the adaptive optics technique to a 39-meter telescope, this is what you would see. So you can see the difference between that and that, right? So it's a huge difference in terms of with what clarity we can see all the details of the distant galaxies or exoplanets or whatever it is we are looking for in the universe with these extremely large telescopes fed by adaptive optics. Okay. So yeah, back to, sorry, that slide was a little bit out of place with my thoughts. But coming back to the point of adaptive optics and the paucity of reference stars, so we don't have as many reference stars as we would like. So as I said, what we astronomers do is we create our own, right? And so this is the principle of laser guide star adaptive optics. So actually we shine a laser from the back of our telescopes that is tuned to the line of sodium. This is the same orange line that is emanated by street lamps, sodium vapor lamps that you see on the street. And because this the solar wind, the rays, that the particles that come from the sun create a layer of sodium atoms in the upper ionosphere of the Earth at a height of 90 kilometers, then when this laser shines into the ionosphere, when it encounters these sodium atoms, it creates a bright spot, thus creating an artificial star. The neat thing about this artificial star is because I'm shooting the laser from the back of my telescope, it is always there exactly where I need it, right? It is right on top of my galaxy. And so now I don't have to worry about the fact that my reference star is not close enough. I can make my own reference star, and with my own reference star, I can get a beautiful adaptive optics correction right at the location in the sky where I want it. It almost works perfectly, not quite perfectly, because of what we call the cone effect or focal anisoplanetism. This is, to give it its proper name, this is the effect that because the star that we have created with our lasers is not at infinity, but at 90 kilometers, it actually doesn't sample the whole cylinder of atmospheric turbulence that we are interested in. It only samples this cone. And so now still there are little bits of turbulence on either side that we cannot sample, but nonetheless, it does a pretty good job. In fact, for the ELT, we will use not one laser star, but what we call an asterism of 6 laser stars in order to stitch together the information about the turbulence of the wavefront from these multiple laser stars. And this is why you may have seen images of lasers coming out from telescopes. The laser light is very narrow band. It only exists at a fixed wavelength and a very narrow range of wavelength. So it doesn't really bother us because we can filter out that particular wavelength from the images that we're taking. So we're not overwhelmed by the laser light, even though it's way brighter than the galaxies that we are looking to see. So here now is the second part of the Gemini movie that now shows you how things work with the laser stars. Here on the side of my telescope, I've got this solid state sodium laser, megawatts of power, all in this one line of sodium. And so now we'll zoom out from the Gemini telescopes. You will see the slit open of the Gemini dome. And from the louvers on the side to equilibrate temperature and wind. And that's the Gemini telescope now pointing where it needs to be. And there you can see the yellow laser being shot from the back of the secondary. We will now zoom out to look head down onto the telescope itself. That's the island of Mauna Kea in Hawaii, now coming into the picture where the telescope, the Gemini North telescope, is located. And now if we go up into the upper ionosphere at high altitudes, and that's where planes fly 10 kilometers. And this is way above that, right? Way above the turbulence. And at 90 kilometers in the sodium layer, you see this really bright spot. It's about 11th or 12th magnitude, not bright enough for the naked eye, but adequately bright for the things that we want to do. Okay, so that was mostly the principles of adaptive optics and of laser guide star adaptive optics, and it highlighted the two main reasons why we are building this enormous telescope. One is to collect lots of light so that we can see really faint objects, and the second is to have a very narrow diffraction limit so that we can take really, really sharp pictures or spectra. Where is it going to be located? It's in the Chilean Atacama. This is a picture of the northern desert in Chile. We like desert because that means it never rains and we can observe all year round. It's cloudless sky most of the time in northern Chile. High up is good because it's above most of the turbulence. The turbulence is actually worst closest to the ground because the ground heats up during the day under the sun's light, and that's what causes the turbulence in the atmosphere. So the higher up you go, the better off you are. ELT will be located some 25 kilometers from an existing observatory, which is where the VLT, or the Very Large Telescope, is located today. That's Cerro Paranal. This will be located on Cerro Amazones, which is the next mountain inland from Cerro Paranal, and construction has started. Right, this was the view from a webcam a couple of years back when the first concrete was being poured in to create the structure. Unfortunately, currently, because of COVID, the cranes are gone. All the work has stalled on Cerro Amazones. We hope it will start back up really, really soon, but Chile is having quite a large incidence of COVID at the moment. So unfortunately, work has come to a halt about 4 months ago at the site. Okay, what's it going to look like when it's finished? Okay, so here's a light path view of the ELT. So I've taken away all of the structure, the tube, etc. All the mirrors are floating in space. The primary mirror is actually made out of 798 hexagonal segments because we can't build a single monolithic mirror that's 39 meters across. So we sort of make these little hexagons and we close pack them so that they will all form the shape of one single huge mirror. And that light gets reflected to a secondary. And then normally it would the secondary would bring it to a focus where the science instruments, the camera or the spectrometer, would harness the light from the telescope. In this case, we need that adaptive optics deformable mirror, which is now built into the ELT. So that's this mirror here, M4, which is 2.4 meters across and will have 5,500 actuators on its back to continuously change its shape in real time. And to get the light to M4, we need this extra mirror M3, which is a spherical concave mirror, and then a flat mirror M5 sends the light out to the side, which is here where the science instrument platform is located. So that's where the instrument that I'm in charge of, Harmony, is going to be located, along with a few other instruments. This platform here is the size of a tennis court. To give you a sense of scale, and the instrument that we are going to put on there weighs about 36 tons. So it's not going to be a small piece of kit. Okay, so here's the light path from the ELT that shows you how it works. So light comes to a focus from the primary, is then a secondary is a convex mirror, goes through M3, the M4, which is the deformable component, and then the M5 flat mirror, which sends this light to the instrument. So let's look at each of those mirrors in turn and see what it looks like. So that's the overall structure. As I said, it's about the size of a football stadium with a 39-meter primary mirror. And the overall thing you can see is about 2,500 tons of steel, which are located with the precision of a fraction of a millimeter, the top of the tube, 65 meters above the ground. And it has to be kept there despite the wind that blows across the telescope, or indeed the desert. So wind loading is one of the biggest, and the vibrations it may cause is one of the biggest headaches that we have to contend with when designing and building the ELT. Okay, so I told you already about this. So here's the 39-meter primary mirror. As I said, it's made of these 798 segments. and each segment is a hexagon. They are made in families, so there is a 6-fold symmetry here. So they are made in families of segments, but otherwise each segment in one petal, one section, 1/6 of the primary, each one looks slightly different because it has to all form part of this huge, enormous parabolic, or actually hyperbolic in this case, primary mirror that is a continuous sheet. So we must try and get these edges to line up precisely to a fraction of the wavelength of light. So that's, asking for sub-micron precision in aligning the edges of these segments with respect to each other and keeping them aligned under the gravity deformation. So as a big telescope like this turns in order to follow different stars in the sky, the self-gravity of these pieces of glass causes things to flex and causes things to deform, so that we need this enormous system of actuators underneath each segment in order to constantly calculate and counteract the effects of gravity as the telescope is moving across the sky, in order to keep the shape of the mirror be precisely that what we want in order to get very sharp images. These segments will be coated with something reflective like a silver coating, but the silver coating wears off under dust and other things that degraded over time because it's sitting there exposed to the elements all night long. So we need a recoating plan. And you can imagine that if we only were to recoat a couple of these segments every day, it would still take us over a year to recoat the entire mirror. So it's a bit like the legendary Forth Bridge in Scotland, that you started painting one side of it. By the time you got to the other end, it was time to paint the first side, time to start all over again. So it's the same with the ELT, in that we have to keep on iteratively recoating a couple of segments every night. So there is a very involved piece of mechanics that is located under each of these primary mirror segments that I'll show you in a second in this movie. So every morning, each of these segments, or the two that are due for recoating, are lifted up. And a big overhead crane comes in, grabs this segment, takes it away to the recoating plant, and a spare segment is installed in its place, realigned to a fraction of a micron with all its other neighbors. So this is now the M2 unit, which is the convex mirror at the top of the 65 meter height, at 65 meters height above the ground, at the top of the telescope tube, and that is reflecting the light to M3. And then M4 is this really difficult to fabricate deformable mirror. So this is also made in 6 petals, and you can see these voice coil actuators, 5,000 of them, that are slowly being populated in order to build a mirror which has this very thin face sheet. So that there is a very thin sheet of glass about 1.5 millimeters thick. And on back of this sheet of glass, we glue these 5,500 permanent magnets, and then the voice coils, which are the same that you have in your loudspeaker at home, are used to actuate and pull and push on these permanent magnets on the back of the mirror, so that we can change the shape of this mirror in order to do the adaptive optics correction in real time. And so this is interferogram showing you how good the quality of the mirror is and how well we can adapt its shape in real time. And that's the final mirror is M5, which is going to just be a flat mirror, but it does fast tip and tilt or image motion correction that allows us to finally direct the light exactly to the instruments sitting on the Nasmyth platform on the side. So these are what the instruments are. So this is a mock-up of all the instruments that are currently planned for the ELT. One of them on this side, this blue and yellow structure, is Harmony, which is the instrument that I've been working with for the last 5 years, and will take us another 5 years to have it built and ready to harness the light from the telescope. The picture on the other side just shows the current telescope, the VLT, placed next to the ELT, and you can see the VLT fits neatly on the instrument platform. So that gives you, again, a sense of scale for somebody who has seen the current generation of telescopes in operation. Okay, well, what are we doing all this for? Of course, is to do wonderful science with the ELT. So I'll just give you, in the few minutes I have left, and give you a brief whirlwind tour of the kinds of things that we are going to be looking for with the ELT. The science case for the ELT rests on three pillars. One is what we call contemporary science cases, which means science we know already, or knew even already before we started building the ELT, that we would want to do. The second is to combine the information we'd get from the ELT with other facilities, telescopes at other wavelengths, ALMA, which works in the sub-millimeter, the square kilometer array, which is a giant radio telescope, which is currently being built in partly in Western Australia, partly in South Africa, James Webb Space Telescope, which will be the successor to the Hubble, and so on. But then I think the most important pillar is the discovery potential. So that's to say things that we don't know how to do yet, right? We don't know what we're looking for. If you just increase the capability that you have to collect light and to make sharp images, you will discover lots of new things, things that you haven't even thought about yet. And that's, I think, one of the biggest drivers for the ELT is its discovery potential. So I can't really tell you much about what we will see on the unknown, but I can tell you something about the contemporary science cases. And those themselves are split into three overlapping themes: planets and stars, stars and galaxies and cosmology. So we start with planets and stars, which is the closest to us in distance. And of course, we all want to know and understand how planets form, how our solar system formed. And now we have discovered about 4,000 odd exosolar planets, so planets that are around other stars, mostly by indirect inference techniques known as radial velocity, or as transit imaging or transit spectroscopy. But with the ELT, with its exquisite diffraction limited resolution, we will be able to take images. They will still show up as single dots of light because we still won't be able to resolve planets around other stars, but we will be able to see the light from the planet separately from the light from its parent star. And that will allow us to look for the presence of elements in its spectrum that we know could perhaps harbor life. You've all heard the talk recently at Khagol Mandal about phosphine on Venus. So that's one example of the kinds of things we could try and detect on other planets around other stars. And then more broadly, of course, the formation of stars themselves and the circumstellar disks that lead to solar systems, and how stars form and what we call their birth function. So how many massive stars do you get, and how many sun-like stars, and how many dwarf stars do you get? Moving on to galaxies, both nearby and distant. To date, the capability we have with our telescopes can only resolve individual stars in our own galaxy, in the Milky Way. We do not have the capability to resolve individual stars in other galaxies. With the advance that the ELT will bring, with the advent of the 39-meter generation, we will for the first time have the ability to resolve individual stars in galaxies nearby, like Andromeda or Centaurus A, which is pictured here. And that will give us a big boost in our ability to study the stars, because once we can identify individual stars and image them separately from their cousins, we can then look at their properties and study their properties in a lot of detail. Moving further away, we can study the phenomena that we know most galaxies harbor enormous black holes in their center, and we can study their physics, their kinematics, their dynamics. The Nobel Prize, as you know, was awarded to black holes this year. Finally, in cosmology, we can look at the galaxies that are really, really far away. And with instruments like Harmony, we can measure through the Doppler effect. We can measure the velocities at which the stars and gas in these galaxies is rotating. And that gives us an estimate of the mass of these objects. So we can essentially weigh galaxies that are 13 billion light years from us, or close to, or up to. And that can tell us sort of how massive they are and how the universe evolved over cosmic time, when the first galaxies were formed, when the first stars were formed. Those are the sort of questions that the ELT will help us answer. Then, as I said, discovery space is one of the primary reasons why we are doing this. And so the ELT excels in both its collecting power, which is as much as all the telescopes mankind has built put together, and it will excel in spatial resolution as well. So the ability to take really sharp images thanks to laser star adaptive optics, and those two together will mean that it will herald a completely new era in astronomy. So I've gone over my time a little bit. Apologies for that. I'll stop here and I'll just leave this movie, which is available on the ESO webpage for everybody who wants to look, which is just a publicity video for the ELT. I'll leave that running, and I'm happy to take questions.
Well, thanks a lot, Sir Thatte, for the very, very excellent talk. I'm very glad to go through the adaptive optics once again. After so many years, I have heard about adaptive optics. There are quite few questions, and I would like to start with some simple ones. Dr. Sujata Deshpande has asked a question, and she would like to know, for example, there could be many celestial objects between us and the object you want to see with the telescope. For example, a star cluster between a telescope and a galaxy. Now, how are you going to correct for those kind of objects which are interfering in your observation?
We can't really see through other objects. Occasionally, if the background object is bright enough, like a quasar, we can actually see the light of it through the outskirts of some intervening galaxy, and that usually actually gives us enormously important information about relatively cold gas that is not emitting light by itself, but is absorbing the light from the background object. But if it is absolutely head on, then we can't really see through it. We can sometimes benefit from an effect called gravitational lensing, which if the quasar is exactly behind a foreground galaxy, it will split its image into multiple images or even into what's called an Einstein ring. And that would give us additional information. So occasionally we can look past other objects, but most of the time we can't. But thankfully, space is pretty much empty. So the chances that we get something else interfering in our line of sight is very small, except if you look straight through the plane of our own galaxy, our Milky Way. And so most of the distant galaxies we observe are typically in the direction perpendicular to the plane of the Milky Way as seen from Earth, because looking through the Milky Way, it's really difficult because it's not so much the stars that get in our way, it's the gas and the dust which scatter and absorb the light. So that really gets in the way of us. But yes, that is indeed a huge problem for astronomy. Hope I've answered the question.
Yeah, sorry, I was mute. So Ashirwad has asked a question, is that since the artificial laser star is of only one wavelength, is it good to have switched capability for the laser and normal distance star?
Yes, so we do both. Actually, I didn't tell you a little bit of detail. The problem with the laser star is that it doesn't correct for something called image motion. So one of the effects of the turbulence of the Earth's atmosphere is that the entire star image appears to move left, right, up, and down in our focal plane. Because the laser star suffers that same movement uplink as it does on the downlink, we actually don't see that image motion to first order. And so even with the presence of laser stars, we do need a natural star in order to sense that image motion and correct for it separately. Thankfully, in those cases, that natural star can be a lot fainter. And so there, having a big telescope like ELT actually helps, because the stars can be enormously faint, 19th magnitude or thereabouts. But so the natural stars are needed. So when we can use a natural star, we do use it because it gives us superior correction. But most of the sky is not covered by the bright natural stars. So then we use a combination of these lasers, guide stars, plus really faint natural stars in order to do the correction that we need. I should stop my sharing and perhaps switch to this view. Then you can see me.
There are two more questions from Ashirwad, and those are mostly related to the operation of the telescope.
Yeah.
The ELT being so huge, are there issues due to the minor vibrations, say earthquakes, which are happening? That's one question. And the second will be there will be temperature variation across the mirror segment. So how are these issues addressed? That's what Ashirwad wants to know.
The temperature variations first. So we try really hard to keep everything equilibrated at constant temperature. This is why we enclose things in a dome because, well, we don't need the dome at nighttime. We try and take as much of it away as we can to let the air circulate freely. Otherwise, we could create our own turbulence. We air condition the mirror, the entire dome actually, not just the mirror, during the daytime so that it doesn't heat up during the day under sunlight. That's also why we paint the outsides white because we don't want them to sit and collect lots of heat from the sun. We air condition them. We also work really hard to keep the glass of the segments all at a constant temperature, which is equal to that of the ambient. If there is some residual turbulence, the adaptive optics can actually correct for it, provided it's a slow enough or large enough scale. And the other question was vibrations. Yeah. So earthquakes are a big problem. Chile is seismologically active, so we have to build all our telescopes and instrumentations to survive the really big earthquakes. But then the really minor ones, well, it's okay if our operation is disrupted during the earthquake. What we don't want is for the operation to be disrupted after the earthquake. So that implies that we have to build really stiff and earthquake resistant structures. Wind vibrations during the night are a big issue, and we have to work really hard in order to make the structures really stiff to reduce the effect of the wind vibration. So in fact, the very early days of the ELT, I was at a big review of the telescope, and one of the reviewers said, where's the dog walking across the telescope? And people sort of looked at him, what's he talking about? It turns out that the weight of a dog is about the wind loading that you would expect on any given segment due to the wind blowing on the telescope primary at night. So if you can keep the shape of your primary mirror intact whilst a dog walks across the primary, then you've got the right level of mechanics to keep your mirror in shape during wind loading.
Interesting, quite interesting. Rupesh Sangoi has a question, and he's saying, how is the field rotation taken care of? Because at such high magnification, because of the alt-azimuth design, wouldn't the field rotation be a problem for the 15-minute exposure that you explained?
Indeed, it is. The field rotates. It rotates on time scales much shorter than the 15 minutes. So we have to rotate all our instruments, or at least our detectors, to compensate. So we do that. Harmony will rotate about a 10-ton cryostat about a vertical axis continuously in order to correct for the field rotation. So yeah, very good question. Field does rotate, and it is an issue for anything other than a very quick snapshot. So you could take lots of quick snapshots and add them together later, but unfortunately our detectors are not noiseless, and so we have to expose for a long time in order to combat the noise, the intrinsic noise from the detectors. Otherwise, we could just take lots of snapshots and put them together afterwards. But yes, we do compensate for field rotation actively by big bearings and big. So we essentially got a 4-meter telescope inside the Harmony instrument because it's turning about one axis all the time in order to follow the field rotation.
Mayank wants to know if the mirror pieces are identical, and does that affect the parabolic shape of the mirror?
They're not identical because as you step away from the center, it's actually hyperbolic slightly, but that's detail of the optical design to keep the aberrations minimum. each segment has to have a slightly different curvature as you go across. If it was spherical, then they could be identical. And we worked hard to try and build them spherical, but the aberrations get to be too difficult to control. Spherical aberration, for those of you who know optics, the owl, which was the 100-meter concept, did have a spherical primary because there was no way you could make different shaped segments for that concept. But for the ELT, there are families. So there are 6 identical segments at 60 degrees apart if you look top down on the primary. But other than that, each segment does look a little bit different. And so, yeah, you have to keep track of which segments where.
In the same line, there's a question from Aditya, and he wants to know why the mirrors are hexagon and why not other shape. But I guess you just now said so.
Well, yeah. So you have to close pack, right? You want to close pack in order to get a complete face sheet which has as few holes as possible, because every hole causes an artifact in that perfect image that I showed you in that airy pattern. So the fewer holes you have, the better your telescope would work. So yes, you could think of close packing with a square or any other regular figure that can close pack. But of course, with a square, because the dimension along the short side and the diagonal is off by a factor of 1.4, it makes it much more difficult to deal with. So you want something that is close to a circle, easy to manufacture, easy to keep track of the edges with edge sensors, etc. So the hexagon is the shape of choice.
This question from Milin sir, and he wants to know, periodically we hear that discoveries of stars with planets that are very far away from us, and they may have atmosphere conditioned to life. So the question is that you said we don't have capability to resolve such individual stars from distant galaxies. So how do we reach that conclusion about atmosphere for these faraway stars?
It's difficult to explain very quickly, but it's through a technique called transit spectroscopy. So essentially, if you think about the star going, the planet around this distant star going in front of the star as seen from our line of sight, then the planet blocks out a small fraction of the light. It could be, as for the Earth, it would be a fraction of a percent. For something like Jupiter, it would be a few percent. For a star which is, for a planet which is fairly close to the sun and very big like Jupiter, the so-called hot Jupiters, it could be nearing 10%. If that planet has an atmosphere, then some of the light filters through that atmosphere, and the characteristic features of the atmosphere in terms of absorption and emission get imprinted on the star's light, or onto the few percent of the star's light that goes through the atmosphere during the transit. And if we are able to disentangle, which we are, that light filtering through the atmosphere of the distant planet while it goes in front of the star in a sort of eclipse situation, then we are able to infer something about the planet's atmosphere. So that's how it's done. But it's mostly still planets within our own galaxy. There are rare cases when people have talked about doing this for objects in other galaxies, but so far, really, most of the exoplanets discovered have all been in the Milky Way.
This question from Aditya, and he says that, we know that there's an expansion of universe is there, and the objects are very far away. So does the expansion of universe cause any difference in the light emitted and the light we perceive?
Yes, it does. So it does affect it. It gets redshifted, right? So because because the universe is expanding, these objects are moving away from us at seemingly very high speeds. And astronomers call this redshift because the light from these objects is shifted to longer wavelengths. And in fact, because we want to study these galaxies, these distant galaxies, in what was emitted as visible light, but which is now shifted to much longer wavelengths in the near or mid-infrared, a lot of the telescopes that we are building and the instruments we are building operate at infrared wavelengths. So for example, Harmony works out to 2.5 microns, where visible light stops at about 0.75 microns. So that's a factor of a few relative to the edge of the visible spectrum. And the James Webb Space Telescope, which is the successor to Hubble, will go all the way out to 25 or 28 microns, because we want to see light which is rest frame visible, was emitted in the visible, but is now observed by us in at much longer wavelengths. So that's the biggest consequence of the expanding universe. Of course, the other is that they are very far away and the light gets fainter the further away the object is.
Josefa Mehta is having two questions. One is, if you have a laser star which is simulated at the edge of the telescope, why not simulate it at the harmony optics itself? That's what is the question.
Guess I don't understand. Josefa, you want to, I don't know if you can be unmuted, if you can explain better.
The question is, if you have a laser star which is simulated at the edge of the telescope, why not simulate it at the harmony optics itself?
Go ahead, Josefa.
I'm just trying to unmute. Okay, she's unmuted.
Niranjan, very nice talk. It just so you have a laser star which is right at the edge of the mirror, and which is actually simulating, providing the differential. But why take it to the optics? Why not simulate it right at the harmony level?
Because the turbulence has been created by the atmosphere. So unless you get the light from this laser star to go through the atmosphere, you can't. So it has to be created above the atmosphere, right, in order for the turbulence to be sensed.
Okay.
And then so it is created at the edge of the ionosphere and also at the edge of the cylinder. The reason it's at the edge of the cylinder is that we have multiple stars like that, and together the cones of all of those stars that I showed you earlier overlap to fill that cylinder over which we are wanting to sense the turbulence, if that makes sense.
Okay. Okay. And the mirrors, are they made at the University of Arizona, which made the remaining Atacama mirrors? Also, the Magellan mirrors were made in University of Arizona.
No, they're not. So Arizona makes monolithic mirrors that are 6 or up to 8 meters in size. These are smaller segments. They are 1.4 meters each, and they are made by Schott in Germany, and they are polished by Safran Reosque in France. It's a European project.
Okay, Srirang, Josefa, if you have any more questions, can please ask, or else we'll move ahead. For two more questions are there. One is from Srirang, and he wants to know, does using multiple laser star reduce the drawbacks of the cone effects?
It does, yes. So, and in fact, the bigger the telescope, the more laser stars you need. So with a small telescope, if you had a telescope that was 2 meters across, one laser star would be perfectly adequate. If you had a 40-meter telescope, you need, we think you need 6. You could think of, so we have an asterism which looks like a hexagon of the 6 laser stars. And there is, you could also think of having a 7th one in the center, which might help. If you want correction over a wider field of view, you need even more laser stars. So yes, we have to stitch together the wavefront. So it takes a lot of real-time computing, because there is a matrix which has to, a matrix multiply, which a computer has to do, which consists of 6,000 odd measurements for each laser star. So we have 6 of them. And those all those measurements have to be turned into corrections for about 5,500 actuators. And this is done with a ginormous matrix multiply, which has to take place within a millisecond, because otherwise it's too late and the correction you applied no longer is relevant.
more questions. I'm sorry, it's getting too many. One is from Milind, and he says, "What is integral field spectroscopy and its importance?"
A topic for probably an entire talk in itself.
No problem.
So integral field spectroscopy is the idea that that's the kind of instrument Harmony is going to be, and it's the idea that in a single exposure you can take an image of a modest field of view in several thousand colors at once, so several thousand wavelengths at once. And it's very efficient because the telescope, of course, collects all the photons of all colors all the time. And it's the ability of, normally the detectors are two-dimensional, so we can only, our detector arrays only allow us to take a picture in one color. The pictures that you see in RGB are actually done by filtering inside your iPhoto or whatever you are using to take your pictures of an intrinsically black and white detector. So most detectors only measure intensity. So if you want to measure color as well, then you have to do something quite fancy, and that's the whole science of integral field spectroscopy. It's also called hyperspectral imaging for people who do it in Earth observation.
And the last question is from Brushal, and he has a question. So to construct such big telescope, is adaptive optics always necessary, or there are any other techniques?
Well, it depends, right? I would say yes, but it depends on whether you are building the telescope simply to gather more light or also to take sharper pictures. Usually the two go hand in hand, but there could be some specialist cases where you are only interested in light collecting area and not interested in sharpness of image. I'd be hard pressed to find one off the top of my head, but in which case you could, of course, not use the adaptive optics. There may also be cases when we can't use the adaptive optics because sometimes there are planes flying overhead and then we have to turn the lasers off because we don't want to shoot them in the pilot's eyes. And other things happen. Sometimes the atmosphere is just not kind enough to us to allow the adaptive optics to work. So occasionally we will want to be able to use the ELT also without adaptive optics, but the expectation is that for this newer generation of telescopes, almost always that we will use the adaptive optics. It's getting more and more common on the smaller telescopes that we have deployed today, but today's telescopes, I would say about half of the time is now used for adaptive optics, or with adaptive optics rather.
Great. Well, thanks a lot. It went on for quite a long time. I'm sure you enjoyed it. We all indeed enjoyed. Ashirwad, are you there?
Yeah, Ashirwad here. I got one question from audience, and that's from Aditya. The question is, when was adaptive optics technology invented, and is it deployed in telescopes in space, probably Hubble?
It was, I think the first one was about 30 odd years ago. And I think the very first adaptive optics was on a telescope in France, in Observatoire de Haute-Provence, if I'm not mistaken. But yeah, it has really come into its own for the big telescopes. You per se don't need it in space because there's no atmosphere, and the main purpose of adaptive optics is to correct for the atmosphere. The one reason you could use it is to correct for small, slow deformations of your optical train, either due to flexure or heating by the sun, etc. But typically that is on much slower time scale. So it's something we call active optics rather than adaptive optics because it's working at much slower speeds. There is no need to do it 1,000 times a second. You can do it once a minute or something. So that's a different kind of correction, but that is useful and is indeed thought about for space telescopes, but otherwise typically not, unless you have a space telescope which is looking downwards, and there have been talk of adaptive optics for those kind of applications, but that's not astronomy.
Great. Well, I think more or less the questions have been done, and it's good to have so many questions are coming from the audience. The lecture was extremely well received. I'm flooded with the messages that kindly convey that it's very nice to hear about this topic, and all astronomers, we all just like telescopes. We just love to have telescopes all around us. And when I hear about a 39-meter telescope, it is mind-boggling. It's indeed mind-boggling. So it's great to listen about the latest developments, and it's great to hear from you. On behalf of Khagol Mandal, I wish to thank Professor Niranjan Thatte for such an excellent talk, and I'm sure he also enjoyed the session, and we wish that you will come back once again with a talk in some near future with a new idea which you might like to share with all the students and the seniors who are joining this kind of sessions. On behalf of all of us, thanks a lot to be here. Thank you for all the audience for participating in this talk and asking so many good questions to the speaker. Well, that's it from Khagol Mandal for the time being. Thanks a lot. Thanks, Niranjanji.
Thanks very much. No, a pleasure, absolute pleasure. Happy to see so many people interested in ELT.
Okay, thanks a lot. Now, goodbye, everybody, and please take care.